Good morning. We're going to continue with our function summary. Now we're going to look at concavity and intervals of concave up, concave down, and inflection points. We use the second derivative to look at that. It's a similar process that we look for increasing and decreasing and relative max, what we used with the first derivative, but we're going to use the second derivative. So first, we calculated the second derivative earlier. We got 18 over the 18 over x plus 3 quantity cubed. I don't know why I had that mistake up there. And f prime equals 0. Well, it only equals 0 when the numerator equals 0, and the numerator is 18, which never equals 0. So therefore, that's easy enough. And f double prime does not exist implies that x equals -3. So that's going to be on our number line. -3, and I have that as double prime does not exist. And then again, x cannot equal +4, so that needs to be there too, because it can't be concave up or concave down or anything at that point because it doesn't exist. And I'll say that this is the sign of f double prime graph. And now we test our intervals just as before. So to the left of -3 in the second derivative, we go and we say we have 18 over a big number cube, big negative number cubes, big negative number. So we have a negative number. Starting with, so I have a negative number there, and that implies, of course, that let's use different colors. Why not? It's more colorful. That implies the second derivative is negative on that interval, so therefore that implies that the original function is concave down on that interval. So from -3 to +4, 0's in that interval. I like 0. The second derivative is positive. We got 18 over 3 cubes, 18 over 27. It doesn't really matter what it is. It's a positive number, which the second derivative is positive on that interval, which implies that the original function is concave up. Now to the right of +4, sorry, the second derivative is, of course, again positive. We just have to, because its original function is undefined there, we have to put that on our interval list. Can't include that in our interval of concave up, even though it doesn't change. It's not an interval. It's not, the function is not defined there. So now we can list our intervals of concave up. It's concave up from -3 to 4, and definitely you can include this. I haven't been doing that anyway. I don't include but these are not inflection points. Well, I mean, I'm sorry, it has nothing to do with inflection points. You cannot include those no matter what, because these are points of undefinition. So normally if the function is defined there, it's kind of debatable. But anyway, don't do that. -3 to +4, it's concave up, and from 4 to positive infinity, it's concave up. Concave down from -infinity to -3. The inflection points are going to happen where your function changes from the second. You can either look at it one or two ways. That the second derivative goes from negative to positive or positive to negative, and the original function is defined there, or you can look at it as, that the original function goes from concave up to concave down, or concave down in this case to concave up, and the original function is defined. Well, we do have a point right there. It goes from concave down to concave up at -3, but not only does f double prime not exist there, the original function does not exist at -3, so there are no inflection points. In fact, we determined earlier that x equals -3 was a vertical asymptote, so none. Just because you have changes in concavity doesn't mean you have an inflection point. That's it. I think all that's left is a graph.